Okay, welcome to discussion here. So, as I mentioned before, what we're going to do during discussion here is we're going to actually continue lecturing. We're going to actually start lecturing out of chapter 5, actually. And that's because next week you have a lab involving chemical reactions and balancing. So, we're going to talk about the balancing part out of chapter 5 here during discussion and the different types of reactions as well, which is technically not even in this book, I think, or chapter, but it is in your lab. So this will hopefully benefit you for next week, and it'll take care of some of the information from chapter 5. So if you want the notes, they are up online for chapter 5, and we're going to kind of go through it. And like I said, it'll sort of serve two purposes. Will help us maybe get a little bit back on track here because of the holiday and all that good stuff. But it also will help you definitely next week with your lab, which involves basically this topic here, which is balancing equations, chemical reactions, and stuff like that. So we're actually going to pick up in chapter 5 notes, sort of in the middle-ish chapter, like maybe the 15th slide or somewhere in that ballpark, where this slide is, and we definitely will go back, obviously, to that stuff as well. In addition, since this is chapter 5, it is not going to be on exam 1 or anything like this, so this would be exam 2 material if you want to kind of mark it. But like I said, the way they have the lab schedule set up, you're hitting this topic next week in lab. So this should hopefully help you with that. Okay, so what we're going to talk about here in this part is we're going to talk about balancing chemical equations and how to do that. We're also going to hopefully talk about and cover different types of reactions or way that you could classify reactions. Again, not really in this chapter either, and I'm not even sure it's still in this edition of the book, but it is in the lab manual and lab. So hopefully, again, that will help you. So let's take a look at an equation. So when we look at a chemical equation, what we see above is what is represents what is known as the balanced chemical equation. And whenever we have a chemical equation, we definitely want to make sure that it is balanced. And what that basically means is there's a law of conservation of mass, which means essentially we don't lose anything in a chemical reaction. The only thing that really happens in a chemical reaction is everybody breaks apart their bonds and they reassemble on the other side. So if you started with, say, 4 carbons, you should end with 4 carbons. You started with 2 oxygens, you should end with 2 oxygens. So this is a balanced equation because when we add up how many hydrogens we have on the left-hand side and oxygens on the left-hand side. On the left-hand side, we have 2 times 2 here, which would tell us we have 4 hydrogens. On the right-hand side, we have 2 times 2, which is 4 hydrogens. Left-hand side, we have 2 oxygens. Right-hand side, we have 2 times 1 here, and that would be 2. So this represents a balanced equation because we have the exact same number of elements on both sides. When we look at a chemical equation, there's a couple parts to a chemical equation. The first part is what is known as the reactants, and the reactants are always on the left-hand side of the arrow. The reactants are your starting materials in a chemical reaction. On the right-hand side are your products. So on the right-hand side of the arrow are your products, and that is what is made as a result of a chemical reaction. Some other things that you sometimes will see in a chemical equation, you'll sometimes see things written up on the arrow. These are what are sometimes referred to as catalysts, which usually will speed up a chemical reaction. You may even see like a delta symbol, which usually means heat. Other things that we oftentimes will see in equations as well is next to the chemical formulas. We may see an S written in parentheses, an L written, a G written. This means it's in the solid state, it's in the liquid state, or it's in the gas state. We also sometimes see AQ written next to something, and this means this is aqueous, which basically means it's a water environment. And you may ask yourself, what is the difference between, say, AQ, which is a water environment, and something that's an L? The difference is if it's an L, for example, if you had water all by itself, that is a pure liquid. If you take something like water and then you take something like sodium chloride and dissolve it into the water, we will get a sodium chloride solution that's aqueous. And that basically is what the difference between a liquid is and something that's aqueous. Typically, something that's aqueous, you dissolve it in something like water, and you make a solution. If something is L, it means it's a pure substance by itself, nothing else mixed in there, just water, for example, all by itself. So when we balance equations, there are some steps here that you can follow, but I'm just going to tell you kind of what people do usually. But first off, though, if you are given something in words, so if everything's given to you in words, you want to make sure that you first start out with the correct formulas and then you balance them. So very often, and it may not make sense now, but maybe later on it may make sense what I'm going to say. Very often what people do is they try to balance it and write the formula at the same time. And what ends up happening is they're so concerned that on the left-hand side, you got 2 of something, I better put that in my formula on the right-hand side just to keep it balanced. And what ends up happening is you get the wrong number of elements on each side. And the rule is you want to start with the correct formula, regardless of balancing anything. Just like you did when you talked about naming and nomenclature, you want to put everything together correctly in the right formula. Then you actually want to do the balancing part. And that's usually the first step that you want to make sure that you do. You want right formula and then balance. Don't try to do both of those things together because you usually will mess up pretty badly. When we balance an equation, we only change the coefficients. So what that means is, again, if we want to balance something like this, we only put numbers up in front, coefficients. We never change the guys on the bottom. We never put numbers like between things or anything like that. So it is only the coefficients that should change. And we want to keep kind of changing the coefficients until we have the same number on each side. Usually what will happen is you'll put a coefficient on one side, it will maybe change some stuff. Then you got to go to the other side, put a coefficient, and it'll change some things. You got to go back to the other side. Most people do sort of a kind of trial and error type of move back and forth. Eventually, everybody should fall into place if you do it right. If you're there balancing everybody and you cannot get it to balance, probably a lot of times this is the problem. You have the wrong formula and you're going to sit there all day and it will never ever balance. So, if you find yourself like, I cannot get this thing to balance for the life of me, you probably have a wrong formula somewhere. And in a lot of cases, that's usually very common. When it's all said and done, what you want to do after you kind of go back and forth is to make sure when everything is done, you have the same number of elements on each side of the arrow, the exact same number for the exact same element. The other thing is when you are done, there's 2 things that also has to happen. All the coefficients need to be whole numbers. And they need to be the simplest set of whole numbers. So you may ask, what does that mean? So for example, let's just say that you balance this equation. Let's find somewhere to write here, maybe something out of the way. Let's say you balance this equation. 2a plus 4b gives you 6c. And we'll just assume that it's balanced. When you look at all those coefficients, they are all whole numbers, which is good. But if you look at all these coefficients, you actually could go through and divide everybody by 2 and reduce it down. And the correctly balanced equation in this case would be a plus 2b gives you 3c. So this sometimes happens because sometimes people can see larger numbers to get things to balance, and sometimes people can see smaller numbers. But if you see a situation where you could take every coefficient that you have and reduce it down and still have whole numbers, you should do that to get the properly balanced equation. And again, sometimes that does happen, kind of based on the numbers that people choose to balance an equation. All right, so these are words. Let's try some here and make sure. So let's take a look at this one here together and walk through the steps that I would take to balance this equation. And hopefully you will as well. But I personally think it's a good idea to take a little accounting of everything you got going on. So we have the reactant side, we have the product side, and we basically have nitrogen, oxygen, and hydrogen in that equation. And we're going to basically count up what we have on each side. And by making this table, it sometimes helps us approach it correctly. On the left-hand side, we have 1 nitrogen. Right-hand side, we have 2 nitrogens, which is the number on the bottom. Left-hand side, we have 1 oxygen. Right-hand side, we have 1 oxygen. Left-hand side, we have 2 hydrogens. And right-hand side, we have 2 hydrogens. So looking at this table kind of helps us decide, doesn't look too bad. The oxygens is good, the hydrogens are good. So this definitely directs us that we should fix the nitrogens. To fix the nitrogen, again, we could only put a number in front. So we're going to put a 2 in front on the left-hand side. When I put a 2 on front, I now end up with 2 nitrogens on the left. 2 times 1 is 2 oxygens on the left and 2 hydrogens on the left. So very much what happens when you go to balance an equation is you fix one thing, but kind of screwed up something else, which is very commonly happens. So we did fix the nitrogen, but we messed up the oxygen. So what we want to do at this point now is logically go to the right-hand side to fix our oxygen. And again, we could do that by putting a number in front, a coefficient. So we're going to put a 2 because we need 2 oxygens. Now, when we do that, on the right-hand side, we still have 2 nitrogens. For oxygen, we have 2 times 1, which is 2. That's good. But now for hydrogen, we have 2 times 2, which is 4. So here again, we fixed the oxygens, but messed up the hydrogens. So to finish this out, we now can simply go to the left-hand side and put a 2 in front of there. And now we will have 2 nitrogens, we will have 2 oxygens, and 2 times 2 is 4. This would represent the correctly balanced equation here. Again, the only number that we changed in any of these was the coefficient, and we didn't even change the coefficient in one of them to begin with here as well. And again, you can kind of see the back and forth, just changing the coefficients, and eventually things should fall into place. Question on that balancing part of it. Okay, why don't you try one and see what you come up with? So why don't you give this one a go? Again, balance this equation, changing just the coefficients, see what you come up with. Okay, so let's take a look and see how we're doing. Again, I would recommend making a table here. So we have the reactant side, the product side, we got carbon, hydrogen, and oxygen. Left-hand side, we have 3 carbons. Right-hand side, we have 1 carbon. Left-hand side, we got 8 hydrogens. Right-hand side, we got 2. Left-hand side, we got 2 oxygens. Right-hand side, we have 2 oxygens there and 1 more there, which gives us 3 oxygens. So in this particular case, not much balance to begin with. So what we would want to start with probably is the carbon. So if we put the 3 in front of the CO2, that's going to give me 3 carbons. In terms of hydrogen, I still have 2. Oxygens, I am now up to 3 times 2 is 6, plus 1 more makes 7. And we're up to 7 in terms of the oxygen. Probably the next easiest thing to balance would be the hydrogen. I got 8 on the left and only 2 on the right. So to fix that, I could put a 4 in front of my water. When I do that, I still have 3 carbons. Hydrogens is 4 times 2, which is 8. Oxygens is 3 times 2, which is 6. And 4 times 1, which is 4. That is 6 and 4, which makes 10 when you add those together. And lastly here, to fix the oxygens, I can now simply go to the other side and put a 5 in front of it. And that's going to give me 3 carbons, 8 hydrogens, and 5 times 2 is 10. So the balanced equation here would look something like this. And again, only change the numbers in front, did not touch any of the numbers in between, on the bottom, anything like that. And again, you may not even have to touch any of the numbers in front and just leave them the way it is. Like normal in chemistry there, anything that is a 1, we typically don't write it. So we don't put the 1 in front of things. So it looks very good there in the chat box. Very good. Question on that particular one there. And again, you can kind of see this is probably the way to do it. Just kind of go back and forth and keep track of everything. Again, people usually find the table very helpful in keeping track of things and also kind of pointing you in maybe the right direction as to where to start in terms of balancing. All right, so let's take a look at another one here. So why don't you give that one a go and balance that equation and see what you come up with. It does not apply to the B, no. Okay, so let's take a look. So same approach. We want to make a little table, and we got B, O, and H. So on the left-hand side, in terms of our B, we have 2. Right-hand side, again, as the question was asked, the 3 does not go for the B, so there's just one of those guys there. For our oxygen on the left, we have 3 here and 1 here, which gives us 4 on the left-hand side. Now, the 3 here does apply to everybody in the parentheses. So it does apply to both of these guys here. So what that would mean on the right-hand side, we do have 3 oxygens because of that. And for our hydrogen, we have 2 on the left. And again, the 3 would be distributed in, and we would end up with the 3. So here we don't have a lot going on in terms of things balanced, nor do we have a lot of options on the right-hand side since all these guys are together. So we might as well start with the B to balance. So very simply, to get that B balance, we need a 2 in front of there. That 2 is now going to give us 2 borons. Now this 2 does also get distributed to everybody behind it. So as we talked about earlier, 3 times 1 for the oxygen gives you 3. Then you need to multiply it by the 2 on the outside. So that gives you a grand total of 6 going on for the oxygen. Same thing will happen for the hydrogen. 3 times 1 is 3. And then 3 times 2 on the outside gives you 6. So if you put the number in front, it goes for everybody behind. But if you have something with parentheses and a number here, it's just for whatever's in the parentheses. But a coefficient goes for everybody behind it in terms of the number. So we fixed the boron. Clearly, we can't play with anything on the right-hand side anymore because it's going to mess everything up. So we might as well look for what might be the easiest to balance at this point. Since oxygen on the left-hand side is in a couple of different places, that might not be the best one to go after next. The best one to go after next would probably be the hydrogen, since it's only in one thing over here, right? So if I change the oxygen, I'm changing a whole bunch of other things. So to fix the hydrogen on the left, we need to put a 3 in front of it. And that gives me 2 borons on the left. Oxygens, I have 3 in the first guy. With my 3 in front on the second one, that now gives me 3 more oxygens. And that is going to give me 6 oxygens. And my hydrogen is 3 times 2, which would give me 6. So by going after the hydrogen here, actually, which is what happens a lot of times, it actually fixed the oxygen for us. So we didn't have to worry about playing with that. It all just sort of falls into place. And usually when you are balancing equations, that's probably what should happen most of the time. You know, at some point after you're done putting in a number of coefficients out there, pretty much everybody should kind of fall into place. Even if you're not trying to balance something, it oftentimes will fall into place. Question on that particular one there. Okay. Why don't you try another one here that we have, I think. So why don't you give this one a go. Try to balance this one and see what you come up with. Okay, let's see how we're doing on this one here. I see something floating through, so let's see how we did. Um, we have our reactant side and our product side in this case, and we have nitrogen, hydrogen, and oxygen happening. On the left-hand side, we have one nitrogen. Right-hand side, we have one nitrogen, so that's good. Left-hand side, three hydrogens there. Right-hand side, two hydrogens, not too bad. And oxygen, left-hand side, we got two. Right-hand side, one oxygen there and one there, and that is two. So on the outset here, doesn't look too bad. Looks like we got everybody balanced except for our good friend hydrogen. So we got two on the right and three on the left. So the common number there is going to be 6 for those guys. So in this case, we actually need to put a number on both sides. So we're going to put a 2 over here. That should get our hydrogen to 6. We'll also probably put a 3 over there. That will get our hydrogen to a 6. In terms of what that just did is we now have 2 nitrogens. 2 times 3 is 6 hydrogens and 2 oxygens. On the right-hand side, we have 1 nitrogen still. Hydrogen, 3 times 2 is 6. And oxygen, we have 1 on the left here and 3 on the right is 4. So much like what usually happens, fix one thing, kind of mess up everything else. So at this point, we can easily fix the nitrogen. We could put a 2 on the right-hand side to fix that. When we put the 2 on the right-hand side to fix the nitrogen, gives us 2 nitrogens. Still got our 6 hydrogen. And in terms of oxygen, now we got 2 times 1 here, which is 2, and 3 times 1 here, which is 3. So that's 3 and 2, which is 5 at this point. So at this point, we do have something that looks like this. It is not balanced. We do need to balance now the oxygen. We clearly don't want to play with the stuff on the right since we already put numbers there. So we do want to go to the left. So the problem is we do need to turn this 2 into a 5. And you can turn a 2 into a 5 a couple of ways, but one way you could do is use a fraction like 5 divided by 2. Because if I take 5 divided by 2 and times it by 2, 2's cancel and I end up with 5. So technically speaking, by going 5 over 2, I now have 2 nitrogens on the left, 6 on the right, and 5 halves times 2 is 5. It is technically balanced at that point. You may be saying, I thought you can't use fractions, and you can use fractions. The problem is you cannot leave the fraction. So even though we could use a fraction here to balance it, we do need to clear the fraction, and we clear the fraction by multiplying everybody there by the denominator, the guy on the bottom. So if I do that, I will end up with 4NH3 plus 5O2 gives me 4NO plus 6H2O. And if I didn't screw up there, since it matches what's in the chat box, I'm hopeful, we should still be balanced. So we do have 4 nitrogens on the left, 4 on the right. We have 4 times 3, which is 12 hydrogens on the left. 6 times 2 is 12 hydrogens on the right. And 5 times 2 is 10 oxygens on the left. 4 oxygens in this guy and 6 in this guy is 10. It is balanced. So this is a very good example that demonstrates that you can absolutely use a fraction to balance it, but you do have to get rid of it by the time it's all said and done. You cannot leave the fraction. This usually occurs when you have an element by itself like we do on the left, and that element's in a couple of other things like it is on the right. How do you pick the right fraction? It's a very simple pick. When you look at the fraction, the top number is always the number you need. So if you remember, we needed 5, so that's why the 5 went up on top. Bottom number should match And what it should match is this bottom number here. So these two here should match. And that's an easy way to remember or choose the right fraction. Top number, the number you need. Bottom number should match the subscript that's to the right of it. And you'll be in business every time. Just got to clear the fraction when it's all said and done. Question on that one here. Try one more here. Why don't you try this one and see what you come up with. Fe SO4 plus Na3PO4 gives you Na2SO4 and should have started it further back, so I'll write it down this way. Fe PO4 and a 2 there, and it should be a 3 there. So give that a go. I'm going to rewrite it neater, but go give it a balance here. Okay, so when you see something like this, it may be like, that looks kind of crazy. There's a lot going on. And you definitely could kind of go element for element like we've been doing on the previous ones. But sometimes if you could recognize that there are these polyatomic ions in here. So for example, if we look at this is phosphate and this is phosphate looking exactly the same. This is sulfate and this is sulfate, which looks exactly the same. Sometimes when you have equations that you want to balance and have these polyatomic ions in it, it is sometimes a lot easier to just keep them together and sort of balance them as whole units rather than go element for element, because then you got to multiply in the parentheses and all those type of things. So in this particular case, I have the same number of sulfates on each side. There's one SO4 on each side. When I look at the phosphate, though, on the right-hand side, there's two phosphates, PO4s. On the left-hand side, there's only one. That's where I would start. So the easy way to fix that is to put a 2 in front. That 2 tells me I now have two PO4s, just like I do on the right-hand side. But when I put that 2 in front, it doesn't just affect the PO4, it also affects the sodium. So I now have 6 sodiums on the left, and that means I only have 2 on the right. So this also tells me where I should go next, which would be I want to come over here and fix my sodiums I just messed up. And I can fix that by simply putting a 3 in front of it. When I put the 3 in front of the sodium here, that helps me with my sodium, gives me 6 sodiums. But it also changes my sulfate that I'm keeping as a group, and that now gives me 3 sulfates. Also tells me I should then go to the other side and fix my sulfate on the left, and I could do that by putting a 3 in front here. Gives me 3 sulfates, also now gives me 3 irons, which if I go to the right-hand side, yay, that's what I needed, three irons as well. So as you can see, it's a lot quicker sometimes, especially if you have these polyatomic ions, to keep them together and sort of balance them as whole units rather than go element by element. You can go element by element like we were doing, but it gets a lot of more difficult, especially with polyatomic ions, because at that point you have a lot of brackets, you got a lot of multiplying in and stuff like that. So again, I would recommend if you could recognize those polyatomic ions, and they do need to be kind of the same looking on both sides, I would keep them together and try to balance them as whole units. It oftentimes will happen a lot faster for you, and it's a lot easier than going element for element. We couldn't do that on the previous ones because we really didn't have polyatomic ions on the both sides or anything like that. But definitely if you have some equations like that, it's usually much, much easier to do it that way. Any questions on that or balancing equations? So the key is you want to have all whole numbers, need to be the simplest set of whole numbers. How you get there is your call. Most people, again, does some type of trial by error, kind of change this guy, change this guy. You know, if you find yourself having to erase a lot of coefficients, something probably not right along the way. Or if you can't get something to balance, think about a fraction. Sometimes you need to use that like we saw. But, you know, the things should sort of fall into place, especially after you put a number of coefficients in there. You know, things should really kind of fall into place. Any questions on that? And again, you can see we didn't change any small numbers, no subscripts. We didn't put any numbers in between things. Only the numbers in front is the only thing that you should touch or change when you're balancing an equation. Any questions on balancing equations? Okay. So we're then going to talk about here for the rest of the time different ways that you can classify reactions. And unfortunately, it's really not in your textbook in any chapter, I don't think anymore, but it is in the lab. So I do want to kind of go over different ways you can classify reactions so that you should be in pretty good shape for next week's lab. So I'm just going to kind of do it by hand like I usually do, since it's not technically anymore in any of the chapters, I don't think, of our book. I'm trying to remember. I don't think it's actually in any of those chapters, but it definitely is covered in the lab. So we'll just do it by hand here. So we're going to talk about different ways to classify reactions. And there are different ways to classify reactions depending on sort of what you're looking at. So I'm going to try to cover from my memory the ones that are in the lab, the way they classify it. So we're going to talk about those types of classifications. So the first type of classification of a reaction is one that is referred to as a synthesis reaction, or it's sometimes called a combination reaction. And in a synthesis or combination reaction, much like the name implies, you basically take two things and you make one thing. So basically a combination or synthesis reaction, two things make one thing. So for example, sodium metal plus some chlorine gas gives you sodium chloride. Two things make one thing, synthesis. H2 plus O2 makes H2O. Two things make one thing. We'll do the balancing. Two things make one thing. Your classic synthesis or combination reaction. Again, those are two types of ways it's called. I almost think your lab manager goes with combination, but some people call it synthesis as well. And basically, whenever you see two things on the left, makes kind of one thing on the right, pretty safe bet that's the type of reaction it's going to be. Now, basically, the opposite of that is what's referred to as a decomposition reaction. And a decomposition reaction is basically just the opposite. You take one thing and you kind of make two things, or more than two things in certain cases. So if we took water and we actually broke it apart into some hydrogen gas and oxygen gas, one thing makes two things. Decomposition, something like carbonic acid will break apart into H2O and CO2. One thing makes two things. They're basically opposites of each other. So synthesis puts it together. A decomposition reaction breaks something apart. So kind of think of them as almost opposites of each other. And again, synthesis puts it together. Decomposition, you break apart. Question on those two types of reactions. And when you're thinking about ways of classifying, this is what you want to look at is sort of the generic way the reaction is and sort of match it up. So again, in this case for a decomposition, you would be looking for one thing on the left-hand side of the arrow and two or more things on the right-hand side of the arrow. While in a synthesis reaction, you would be looking for two things typically on the left-hand side of the arrow and only one thing on the right-hand side of the arrow. So that's a way you could kind of identify those things. The next type of reaction is one I believe that you have, which is what is referred to as a single replacement reaction. And in a single replacement reaction, you have A plus BC. Now, if A is a metal and B and C is an ionic compound, so a positive and negative guy, so an ionic compound here. Now, we talked about metals, and when they do form charges, they do form a positive charge. When it's over here by itself, it has no charge. But when it does make a charge, it is going to be positive. So what's going to happen in this reaction is the metal will come in and kick out the positive guy. And what will happen is the metal will then get a positive charge and hook up with the negative guy and make a new ionic compound. And the B will come out by itself and end up with no charge over here. So an example of that would be if you took a piece of zinc metal and you react it with hydrochloric acid. Hydrochloric acid is positive and negative. And what's going to happen is the zinc here has no charge. It's going to come in. It's going to kick out the hydrogen. When it kicks out the hydrogen, that is when the zinc will gain its normal charge of +2. And it will hook up with chlorine, which has a charge of -1. And those guys will come together to make zinc chloride. When they come together, just like we talked about with nomenclature, equals 0 when we put that together. When hydrogen comes out, it comes out as it would in its elemental form, which is H2 or hydrogen gas. When you do this experiment or this reaction, you will see bubbles. And those bubbles that form is the hydrogen gas that's being generated. This is not balanced. You need like a 2 there to balance it, but this is a classic single replacement reaction. In order for this reaction to happen, whatever is coming in needs to be more reactive than what it's replacing. So for example, if you did the same reaction with copper metal and you did some HCl, when this reaction would take place, you would get no reaction. And that would tell you that copper is less reactive than hydrogen because the reaction did not take place. What we know above here is this reaction takes place, which means zinc is more reactive than hydrogen because this takes place. Again, here he would come into this guy because copper does not have a charge here, but when it does have a charge, it is positive, so he would replace the positive guy. So this is your classic single replacement reaction. It actually also happens with a non-metal. So you can have A plus BC, same setup here. This could be a non-metal. And the same thing is going to happen. The A, which does not have a charge, so this guy has no charge here, he will come in and actually kick out the negative guy. Because as when we talked about, the non-metal makes a negative charge. And when he does, the positive guy and that new guy coming in will make a new ionic compound. And C will come out with no charge on this side. Same thing has to happen. The guy coming in needs to be more reactive than what it's replacing for that to happen. So for example, if you took Cl2, chlorine, and you react it with sodium bromide, how do I recognize this? This is chlorine by itself, has no charge. This is an ionic compound, metal, non-metal. So right there, it should look just like what it does above. And what's going to happen is the chlorine is going to come in and kick out the Br. When the chlorine comes in, that's when the chlorine will get its negative charge. Its normal charge, the sodium has a positive charge. These two guys will come together to make sodium chloride. The bromine will come out, and when bromine is in its elemental form by itself, it's one of those diatomic molecules. It has no charge over here. And also we want to do some balancing, a 2 there and a 2 there. And this is a single replacement reaction. What we would be able to determine in this case, chlorine would be more reactive than bromine if this reaction did take place. So a single replacement reaction, the way you recognize it is you have some element by itself, no charge, and you have a positive negative guy. And that's the way you could recognize a single replacement reaction happening. Again, by itself element, no charge, positive negative guy, just like on the previous page. Element by itself, positive negative guy. Element by itself, no charge, positive negative guy. That is the way you could definitely recognize it being a single replacement reaction. Any questions on single replacement reactions? The next type of reaction classification that you have is a double displacement reaction. And the way that you could recognize a double displacement reaction is this way, AB plus CD. What makes these guys special is this guy will be an ionic compound, positive, negative guy. This guy will also be an ionic compound, positive and negative. So this is the way you could definitely recognize a double displacement reaction. You're starting with 2 ionic compounds on the left-hand side. And what happens in this case is the 2 positive guys, they basically switch partners. That is basically what will happen in this reaction. So A that is positive will hook up with D that's negative and make a new ionic compound. And C that's positive will hook up with B that's negative and make another ionic compound. So if you took something like sodium nitrate plus, that's not right. Let me rewrite that there. Hang on. That's not what I wanted to say. Take 2. Here we go. If you take something like sodium chloride, which I think is what I was trying to spit out there badly, take sodium chloride plus some silver nitrate. When we look at this guy is positive, this guy is negative, this guy is positive, this guy is negative. That meets our criteria of double displacement. So what's going to happen, and when you have to predict what goes on the other side, you just want to think about what are the basic units here. So sodium is sodium with a +1 charge, like we talked about in the naming. Chlorine is a chloride with a -1 charge. Silver is a +1 charge. Nitrate is a -1 charge. So again, they're going to switch partners. So this guy's going to go this way. this guy is going to go this way, and we will get NaNO3 plus some silver chloride. And this is a classic double displacement reaction. Our two positive guys switch partners. And that's one way you could classify this. By the way, when silver and chloride come together, it makes a white solid. And it usually will have a little S next to it for the solid. And because it actually makes a white solid, sometimes double displacement reactions are also called precipitation reactions, because a precipitate is a solid. So a precipitate is basically that solid that is formed. And we'll talk in a later chapter how you know that's going to be a solid. We'll talk about that in a later chapter, but it's sometimes called a precipitation reaction. In terms of the classification for your lab, I believe they stick to just double displacement reaction, but it's also sometimes referred to as a precipitation reaction as well. So if we look at like the one that we had earlier, where we had this guy that we balanced, we had the FeSO4 plus our Na3PO4. Again, if we just saw the front part here, this is positive, this is negative, this is positive, this is negative, and that classically looks like a double displacement reaction, and it is. And I put it up like this to explain what I was talking about earlier. Sometimes people, when they go to put the guys on the right-hand side, they try to balance it and write the formula. So when you have something like this, this is iron 2 sulfate, which means it is made up of an iron with a +2 charge and sulfate with a -2 charge. This is sodium phosphate. Now, even though there's 3 of those sodiums, sodium has a +1 charge and phosphate has a -3 charge. I can't tell you how many people, when they move it over, decide I need to keep the 3 over here because, well, there's a 3 on this side for the sodium. So when you're trying to put it together correctly, this is what you want, the basic units. And you want to put these guys together correctly, just like you would have done with nomenclature, which means when I put the iron with a +2 charge together with the phosphate with a -3 charge, that is how I get to the correct formula of Fe3PO4 2. 3 irons at +2 each gives me +6. 2 phosphates at -3 each gives me -6. That is the correct formula. Even though there's only 1 iron on this side, there's 1 phosphate on this side, I need to have the right formula here first before I balance it. And then my second guy would be the sodium, that's +1, and the sulfate, that's -2. And that is how I get to Na2SO4. Again, I have a 2 here, but a 3 here. I am not concerned about that at this point. Once I have these proper formulas here, now I could go like we did earlier, back and front, and put our right coefficients in front, and it will fix everything that we need. Again, that's why we put the 2 here, the 3 here, and the 3 here. But that is the order I was talking about earlier. You want to make sure you get the right formulas, which are based off of the basic units of everybody. You want to get the correct formulas down. Then you want to balance. I can't tell you, like I said before, how many people will go, well, I got the 3 there, I better keep it. So that looks good. And on this one, like that, looks good. Because I just put them together. And I kept all these 3s to balance everything. And this is not the right formula. This is not the right formula. And you'll be there all day trying to get something to balance that probably will not balance. So that's what I was kind of talking about earlier, where I said you want to make sure that you first get the right formulas down, then go back and balance. So you want to do it in that order. Otherwise, again, you'll run into a lot of trouble along the way. Question on that type of reaction, which again is a double displacement. The way that you could recognize that is you start with 2 ionic compounds on the reactant side. Okay, one last classification, which I think is the last one that you have, and that is what is referred to as a combustion reaction. And There's two types of combustion reactions. The first type is what your lab manual talks about and even your book. The general definition of a combustion reaction is it involves O2 being present. So if you had something like magnesium plus O2, makes some magnesium oxide, a little 2 there, a little 2 there. It has O2. It technically is a combustion reaction, and you could classify as a combustion reaction because of that. We could also, if you look at this, that's two things that make one thing. You could classify this as a synthesis or combination reaction as well. And with reactions, you actually can classify the same reaction a couple of different ways depending on what you're looking at. Kind of like what we just saw with the double displacement reaction was also a precipitation reaction. Most people would probably for this one go with this definition, but technically it meets the general definition of combustion, which basically means there needs to be O2 present. When most people think about combustion reactions, they think about sort of what is sometimes referred to as the organic combustion reaction. And in an organic combustion reaction, an organic molecule contains carbon, hydrogen, and oxygen. And whenever you see something that's organic, that has carbon, hydrogen, oxygen, and O2 present, it will always make CO2 and water. That's a pretty no-brainer there. That is what you're going to get in this organic combustion reaction. And these are the three things that you see: O2 on the left, CO2 and water on the right. So for example, the CH4 plus O2, CO2 and water. This is a classic combustion reaction. This is actually what happens when you light a Bunsen burner. The methane comes out of it and mixes with the O2 in the air. You give it a spark. It's very flammable, right? A lot of organics are methane, propane, butane, right? When we're barbecuing and all that good stuff. So this is probably 9 times out of 10, what people would probably look at in terms of combustion reaction is this one. And in an organic combustion, those three things are always present, always on this side is what you get. But again, in your lab manual and in other books, a general definition is you just need some O2 present, and it will be technically classified as a combustion reaction. So probably in our class, in the lecture part, in terms of combustion, the bottom one, the organic one, is more how we would probably classify it. But like I said, the general definition is O2 present. I think, if I'm not mistaken, that should be all the different types of classifications that's in your lab manual. So you should be good to go for next week's lab. You should now know how to balance equations, write equations. You should know how to classify equations. And unfortunately, I would reference you to the book in terms of classification of reactions, but I don't think it's in the textbook anymore, those things. The balancing part is in chapter 5, so it is in chapter 5 if you want to look at chapter 5, but the classification part is not. Any questions on that before we wrap it for tonight? A reminder, just like I said in lecture, the exam will be moved from next Wednesday to the following, so 2 weeks from today. It will cover chapters 1 through 4, and we will continue lecturing, obviously, on Monday. Other than that, if you didn't put here, please do so, and have a good weekend and all that good stuff. I will see you next week.